MET 345 Test 1 Review. Section 1, Types of Cyclogenesis. One quick note is that you should know the synoptic setup involved with each of the following, which I'll go over now. Firstly, you have olographic cyclogenesis. Orographic just means essentially related to mountains, and they can also be called Lee cyclones. These result from low-level flow, about the surface to 850 millibars, that is perpendicular to the mountains, meaning it flows down them, down their lee side. And as these winds flow down the mountain slope, the flow is stretched vertically and the column grows thinner and stretches upward. This increases low-level vorticity, think of the ballerina or ice skater effect, and can be spread out via vorticity advection. It forms both a lee trough and an orographic low. Remember that troughs aren't the same as lows. The lee trough can form outside of frontal zone, but an existing front to the west may move into the orographic low. A lee trough can form despite negative vorticity advection or ridging aloft. As long as the low-level flow is blowing against the mountains, which will give surface pressure falls. If the positive vorticity advection with the upper trough moves over the lee trough, development will continue. Otherwise, the lee trough will die out as low-level flow becomes parallel to mountains. It doesn't remain perpendicular to them forever. The orographic low will move away from the lee side of the mountains as upper-level positive vorticity advection moves eastward. The most common place for something like this is near the U.S. East Coast by the Appalachian Mountains. Next up, we have type A versus type B cyclogenesis and the differences between them. So, to tell the difference, they differ by distinguishing features in the fields of motion and pressure and on the frontal pattern present elsewhere or around them when the new cyclone emerges. So, for type A appears as a cyclone wave along the front of a cold outbreak, and it appears when there is a cold anticyclone covering most of the U.S. east of the Rockies. It appears along a continental polar air mass flowing off the continent to the east. There's a semi-permanent high in the Atlantic that blows maritime tropical air from the southeast, which steepens the temperature gradient in this area. A portion of the cold front is slowed in such a way that it gives the appearance of a wave. Over the slowing portion of the cold wedge, there is a spreading of middle clouds and precipitation. And for type B cyclones originate near the east coast, southeast of an older cyclone. So remember this distinguishing feature for them. They surface along the warm front of the older storm, and due to topography, it's more unique to the east coast. It occurs when there is an occluding or occluded primary cyclone near the Great Lakes, either stationary or moving northeast. There's a shallow wedge of continental polar air associated pressure wedge between the Appalachians and the Gulf Stream, extending southwestward to form a cold anticyclone. This shallow cold air remains along the coast. There is a maritime tropical air mass flowing from the south against the cold wedge, leading to a front between two air masses. Clouds spread over the cold wedge, separate from the primary cyclone. And as the new cyclone forms, local areas experience pressure falls ahead of the primary cyclone, and this new cyclone becomes a nor'easter. So just as a quick recap, remember that essentially the synoptic setup for type A would be when there's a cold anticyclone covering most of the U.S., and it doesn't require an older or parent cyclone to form, whereas B just forms off of the back of an older cyclone that's around the Great Lakes area and doesn't involve any sort of anticyclone being necessary in the U.S. east of the Rockies to form. Next up, we have coastal cyclogenesis, and this occurs along the coast of the Carolinas. It features a sort of jump of the surface low. This occurs where there's a low-level jet near the coast that transports warm and moist air from the Gulf Stream. It sometimes occurs in advance of the development of a separate 850 millibar low. It's often associated with a pre-existing subtropical jet streak and or coastal front, and it is not associated with earlier major surface cyclones. Next up, we have explosive or bomb cyclogenesis. And just for some definition reminders, these are extratropical cyclones whose surface pressure falls at an average of at least 1 millibar per hour for 24 hours at 60 degrees north. And remember that as latitude increases, the pressure drop per hour needed to be categorized as a bomb increases as well. They occur most frequently in January and February over the eastern United States. They're most common over the westernmost portions of the Atlantic and Pacific Oceans, 5 to 10 degrees north of the zone of maximum winter initial cyclogenesis. These are so intense that they often feature an eye-like clear area near the center, similar to a hurricane. And looking at a 500 millibar map, the trough is going to be southwest of the surface low, and about 1/4 of the way from the trough to the ridge is where bomb cyclogenesis is going to be favored. It's aided by strong diabatic heating and the relatively smooth ocean surface when forming over water. It occurs in areas of most intense sea surface temperature gradients, or SST for short. Next up, we have polar lows, which are also sometimes called Arctic hurricanes. They're small synoptic scale cyclones in the polar airstream behind a main polar front, and they have the typical comma-shaped cloud pattern. If there's a small distance between the comma cloud and a wave on the front to downstream, they will combine on the satellite image, which ends up looking like a mature occluded cyclone. This is called instant occlusion. These occur over water in the presence of conditional instability due to warmer SSTs and cold air. It functions similarly to lake effect in that sense. Lastly, we have marine cyclogenesis. And marine cyclogenesis occurs over water, of course, and is found along a broad baroclinic zone of about 400 kilometers wide. The following three major aspects of marine cyclogenesis do not fit the classical model of the Norwegian cyclone. So first, you have the loss of cold frontal baroclinicity or frontolysis near the cyclone center during the early phases of cyclogenesis. You have the subsequent westward migration of warm frontal structure back into the northerly flow west of the intensifying cyclone. And you have the formation of a warm core frontal seclusion in the post-cold front air in the fully developed cyclone. So just the development stages of the marine cyclone. Stage 1, you have the incipient frontal cyclone. This forms along a broad, about 400 kilometers wide, zonally continuous frontal zone, just like a regular cyclone. So an area where cyclogenesis is going to be favored, a baroclinic zone. Stage 2, you have frontal fracture. This is usually within about 12 hours of the previously continuous front. And at this time, it fractures near the center of the intensifying cyclone. The temperature gradients at the warm and cold fronts have contracted in width to about 100 kilometers. Stage 3, you have the bent back warm front and frontal T-bone. Here, the cold front advances eastward into the narrowing warm sector, while the warm front develops westward in a storm relative sense. So relative to the storm's location, not a specific latitude and longitude on the Earth. Frontogenesis is occurring in the northerly flow to the rear or west of the cyclone within the cold polar airstream behind the advancing cold front. The warm front is being bent back to the west while the cold front is oriented normal to the warm front, and this forms a frontal T-bone shape. In marine storms, this stage is reached by about 18 hours, or 6 or so hours after stage 2. And finally, you have stage 4, which is warm core frontal seclusion. At about 24 hours, the cyclone is at maximum intensity and the cold front has advanced about 500 kilometers east of the center. The bent back warm front and cold polar air have cyclonically encircled the low pressure center of the storm. A pocket of relatively warm air is found at the center of the low and is termed the warm core seclusion. It is an anomalous region of warm air that forms within the baroclinicity of the polar air and does not involve air originating from the cyclone warm sector as typically depicted in the Norwegian model. The warm air was already there. The cold air simply encircles it. Next section, we have non-classical synoptic scale features. So we're going to go over the distinguishing characteristics of the following, and just like before, you should know the synoptic setup involved with each of them. So firstly, we have anafronts and catafronts. You don't have to focus much on these, but just remember that cats are very agile and don't like water very much. What we'll instead be focusing on is cold fronts aloft, or CFA. These appear similar to a catafront, and it includes a warm or arctic front at the surface and to the north, a cold front aloft which produces the main precipitation, and a surface trough. And the surface trough usually lags some 2 to 300 kilometers behind the cold front aloft's leading edge. So how would you locate a cold front aloft? So you would locate it by seeing that the main precipitation is located ahead of a surface trough, or above the precipitation region, there is a larger than normal temperature gradient. The cloud band is located on satellite ahead of the surface trough and along the cold front aloft. Behind the cold front aloft, cloud tops rapidly decrease in height, as another indicator. And you should also see 700 millibar cold air advection ahead of the surface trough. Cross sections of theta E wind and temperature also indicate a cold front aloft. Next, we have upper level frontal zones, and these are associated with high static stability, or where the isotropes are compact. You also have strong horizontal and vertical wind shear, so just wind shear of any kind that's strong, and high values of ozone extruding down along the frontal zone from the stratosphere. Here is where an exchange between stratospheric and tropospheric air takes place. Finally, you have instant occlusions, and this is a name given to the lambda-shaped cloud pattern produced when a cloud band associated with a polar trough interacts with a cold band associated with the polar front. It occurs when the common cloud merges with the downstream synoptic scale frontal system, giving the appearance of an occluded system. So up next, you have things from Chad's talk. And firstly, to just explain the goals of the research and why we do this study. This research was meant to explain how atmospheric processes come together to create moisture, lift, and instability or heavy snow along the coast. It's meant to answer questions like, why didn't we get snow in the big cities? Why was it a quote-unquote bust? And what was different? When are things just a close call? And we can use this research to improve weather forecasting in the following way. We can obtain a numerical representation of the CM. We can quantify things and take averages, etc. And we can decide which atmospheric fields will be used to assess the CM. And we can identify events similar to the CM. We can also use it to establish critical thresholds that determine whether something will be a false alarm or not. Next, we ask, what are the major differences between the quantitative conceptual model and the false alarm composite? The QCM took the average of 44 lows and found what features they had in common. The potential false alarms found 84 lows along the coast, but did not precipitate heavy snow, or precipitation was non-existent. And these both analyzed the same place at the same time and at almost the same path. The main differences were that the potential false alarms had somewhat weaker troughs and maybe a weaker surface low, weaker in magnitude for its 850 jet. And a key feature difference is it is lacking in the strong U component of the wind, which is responsible for advecting the warm, moist air offshore needed for snow. It showed weaker temperature gradients too. At the end of the lecture, Chad concluded that they lacked strong onshore flow, which advects warm, moist air for heavy snow. Up next, we have the section titled Forecasting Methods. So firstly, you should be able to explain how the CIPS analog guidance is constructed. And this analog is constructed by searching climatological data set for maps that resemble the current forecast. It is then assumed that these maps will evolve in a similar fashion to that of the past map. And how can this be used in operational forecasting? It's not meant to make forecasts, but simply to provide some basic guidance for heavy snow or winter weather events to forecasters. And next, you should be able to explain the standardized anomaly guidance and how it's constructed. And this is constructed by taking an individual data point and determining how many standard deviations away it is from the mean of all the other data points. For example, a standardized anomaly of -3 means the field is 3 standard deviations below the mean for that point in time at that location. And how can it be used in operational forecasting? It can be used to determine exactly how anomalous any given weather event or associated data point is. For example, a temperature deviation from the mean of 10 degrees Fahrenheit is more anomalous in July than January. So it's important to know that the standard deviation value instead of just the temperature value in that case. Next, we have the section Basics of Precipitation Types. So, the Cedar-Feeder effect and the temperature we look for to confirm that clouds have ice. So, to confirm clouds have ice, we look for temperatures of -12 degrees Celsius or lower to confirm cloud ice. And the Cedar-Feeder relationship is when ice crystals are generated aloft and then fall into a lower level cloud with supercooled water. You can get freezing drizzle with no layer above freezing due to supercooled water. It can occur at temperatures as low as -5 degrees Celsius because it can fall in the form of supercooled water droplets that freeze upon making contact with the ground. So there are 2 ways in which ice pellets or sleet can occur. And the first way is more common and the second one is more rare. So the first way, snowflakes partially melt in an elevated warm layer and then fall into a sub-freezing layer at the surface. And since it's only partially melted, no renucleation is required. However, the second way is when fully melted particles fall into a very deep and cold surface layer. And this has to be at least 0.5 to 1 kilometers deep and about -10 degrees Celsius or less. So freezing rain is self-limited because as ice melts into liquid, it cools the atmosphere due to the latent heat. It expands to melt. This may result in the entire column being cooled, which just gives you snow. And as far as what can prolong freezing rain, remember that water has a very high specific heat, meaning it takes more energy to change its temperature. So if the warm layer is drier, then it will cool more rapidly and the freezing rain won't last as long. But if the warm layer is closer to saturation, it will take longer to cool and thus prolong the freezing rain. So final section concerning jet streams and jet dynamics. First, you just have the definition of jet stream, and this is a quantitative definition, and it is an intense, narrow, quasi-horizontal wind current associated with strong vertical wind shear found at or near the tropopause. Quantitative specifics, it has to be at least 60 knots or 30 meters per second for the upper troposphere or 30 knots or 15 meters per second for the lower troposphere. It has to be at least 0.5 to 1 order of magnitude wider than its length. And vertical wind shear must be at least 0.5 to 1 order of magnitude greater than synoptic scale wind shear. And this should be at least 5 to 10 meters per second per kilometer. Next, we have the basic characteristics of all the jets. So for the polar front jet, it's associated with the polar front that meanders across mid-latitudes. And meanders simply means that it looks more wavy than straight. It's found near the tropopause at about 150 to 400 millibars. And the polar front jet will be higher up as you go further south in the northern hemisphere. It reaches lower latitudes in the winter, down to about 30 degrees north, but in the summer, it retreats up to about 50 degrees north. Next up, we have the subtropical jet. And this is located near 200 millibars and does not meander much, meaning it's more straight. It's further south than the polar front jet, and it occurs at higher levels than the polar front jet. It's mostly only a winter thing and is found between 20 north and 35 north. Keep in mind that it may be difficult to distinguish from the polar front jet sometimes, but both jets have two separate jet cores. It is not associated with strong temperature gradient and can't be explained using thermal wind theory. Instead, it's mostly explained by the conversion of angular momentum as air as it moves north and south from rising air columns over the equator. This is associated with the Hadley cell circulation that we learned like first year. Next, you have the low-level jet, which is usually found in the Midwest at winds greater than 30 knots, typically from the south. There are two types. One type is found at the exit region of an upper-level jet at about 850 millibars, and the second type is associated with the Midwest topography. Don't worry too much about it, as it will be discussed in a later part of the course. So those are the types of jet streams. Next, we're going to discuss what causes jet streaks. So jet streaks are caused by strong horizontal thermal gradients. And according to the thermal wind equation, higher horizontal thermal gradient means higher vertical wind shear, which results in stronger winds aloft. The horizontal thermal gradient increases with confluence of the geostrophic winds, which compacts the thermal gradient. Remember that confluence is not equal to convergence. So, characteristics of the jet entrance region. Remember, escalator, not elevator. In the jet entrance region, warm air rises in the divergent quadrant and circles around the jet entrance toward the cold section, where it then falls and circles back around under the jet. Impacts of diabatic heating and approaching shortwaves on jet streaks, and this is associated with the backbuilding of jet streaks. Jet streaks are backbuilt when their entrance region stays in place, even as the core moves downstream. This happens as a result of diabatic heating caused by precipitation in the divergent entrance quadrant. It warms up the warm section, which keeps the temperature gradient strong enough to keep that jet streak strong. And finally, we have the revisions that you must make to the four quadrant models when there's curvature involved. So there's a trick to remembering this. It's pretty simple. When the jet streak is curved, only half of the four quadrants, or just two of them, will actually involve convergence and divergence. And it will be about the same, they'll be in about the same place as if it was all four quadrants in a straight line. And how do you remember where they go? Just think about the curved jet streak as a banana split. So obviously on a banana split, the bananas are at the bottom and all the good stuff is on top of them. In this case, the good stuff is the convergence and the divergence. So on the inside of that banana-shaped jet streak is where you'll get convergence and divergence in the typical spot that you'd normally see them. And then just a quick note on jet coupling and how vertical motion is pumped up when it occurs. So jet coupling is when two jets couple, as the name would suggest, and both of their divergent quadrants overlap. So the divergent entrance region and divergent exit region of the two jet streaks overlap, and this leads to amplified rising because obviously there's going to be more divergence in that area.